So now I want to just look at a larger scale and think about the movement of water from an ancient water table below the surface. So this is going to be evaporation from a deep water table. And we have to build this up piece by piece. So here's going to be our elevation. And right here, we have some water table at some great depth. Okay? Now, here's the surface of our soil. So this is a land surface, okay? And what we're going to assume is this has been drying for quite some time. So there is some little depth here, which this we will call the water-free, the liquid water-free zone. Liquid water-free zone. So this is completely dry. But the relative humidity of the air, it's a desert. It could be, say, on the order of 20%. But we know in the liquid zone, which is below here, we know that the relative humidity here is about 100%. Okay, so what we end up with then is a gradient in relative humidity. So the flux here, the vapor flux, we can call that as J vapor, is equal to the diffusion coefficient for water times the gradient in humidity. Okay? And so, of course, the gradient in humidity will be something like 80% relative humidity over this depth of the dry zone. Okay, so we'll call that depth D1, if you will. Okay? So what we have then is a region where vapor is the only driving force. Now, this flux has to be supplied from below. Okay, now let's look at where that flux comes from. One of the things that we have in deep unsaturated zones is a temperature gradient, and we call that the geothermal gradient. And that's a gradient in temperature. So typically the Earth is warm in the middle and cooler on top. So we're going to go ahead and draw a gradient in temperature here. I'm just going to kind of go like that. Okay. So we have a T at the water table, and we have a T at the surface. And there's a gradient. And typically, let me have T water table. Okay, and so we'll put our, sorry about that, the water table fell off the bottom of the screen. Okay, so we have our water table here, and typically that will be fairly constant, that gradient, because it's dependent on, there's this energy flux going out, and because the thermal conductivity of the subsurface is more or less homogeneous, then since the same amount of energy is going out at all times, then the gradient is the same because it's carrying to have conservation of energy. So same in, same out, constant gradient. Okay, now, the interesting thing is now we need to look at what is driving vapor flux in this region. So the vapor flux in this region is going to be due to the change in saturated humidity. The point is that when there's higher temperature, the air can hold more water. So there's what's called the psychrometric curve, which says that the amount of water vapor as a function of temperature. So this would be 0 degrees C, and this would be, say, 35 degrees C. And what we see is that this is essentially an exponential curve. So even though the gradient of temperature is constant, because the saturated water content of air goes up very rapidly as it gets warmer, in fact, the humidity curve is not linear. The humidity curve bends. So what we have is we have a rapid change in humidity at the bottom because we're in this region where it's very warm and the saturated humidity changes quickly with temperature, whereas at the top it changes more slowly. So what's happening then is we have the same diffusion here, but the gradient in vapor concentration is actually bigger change in vapor concentration per unit length than here. So we have a high flux, a high vapor flux here. In the low region, and we have a lower vapor flux here. Okay, so what we have going then is that because of the thermal gradient, we see that there is a gradient in the humidity of the air. And that gradient in the humidity of the air gives rise to a flux of gas. And so, but there's a high flux here and a low flux there. What does that mean? How would you go from a high amount of water moving here, lower there? What's happening is this water is condensing. So the extra water condenses. Well, this is really interesting. So what we have is water is coming off the water table, going up, but it's condensing as it goes. So in fact, what we're getting in this region is a downward water flux. Because more and more water is condensing as the water vapor comes up. So what we have then is a downward flux here that redelivers water to the water table. So water vapor goes up and comes down as liquid. So this then becomes a constant flux. So in this whole region, we have a unit gradient. And what we learned in the unit gradient flow is that means the pressure is constant. Remarkable. So we might have thought, when we first looked at this, that the water content would be driving, the water would be running as water films, but that doesn't work. There's not enough negative potential here to drive liquid water up. But because of the thermal gradient of the Earth, it drives water vapor up. Unfortunately, as it cools, it doesn't hold as much water, so that water condenses and then runs back down. So this cycle of water vapor up, water down, is driven by the geothermal gradient of Earth. When it gets to this point, the gas flux here is matching the gas flux delivered plus whatever rate of decay of this surface between the liquid water and the freeze zone. So if it happened that this flux was exactly equal to the gradient in the gas flux here, this would stay at a constant level. If, on the other hand, this had a greater gradient in humidity, which it generally will because it goes from very dry to moist, it's going to eat up this extra liquid water which is staying behind, and slowly this surface will penetrate further and further down. And so this will slowly drop down, but the key point here is the geothermal gradient gives rise to a uniform gradient in temperature, That gives rise to a decreasing gradient in humidity with high vapor flux at the bottom, lower vapor flux at the top. That gives rise to the condensation as you go, and so downward liquid flow. So in our deep vadose zone, we have a cycle of water vapor driving liquid water, and then finally a ever deeper penetration of the dry zone as it uses up all of the vapor flux delivered from the deep water table, plus consuming the liquid water that's left in the soil here. So this thing is slowly dropping in depth, decreasing pretty much linearly as this depth goes down. This flux drops, and then eventually with this coming all the way down. But the point is that for systems which are on the order of hundreds of meters deep, this flux is on the order of fractions of a millimeter per year. And so this whole process means that the drawing of deep deserts takes literally hundreds of thousands, if not millions of years. And so it's a real geologic process rather than a process which really influences the hydrologic system.